Well, good evening, and thanks for inviting me to speak here. So I'll try to give you a talk regarding some of the current situation in semiconductors and EDA, and what a little bit of what we can expect in the relatively short term and that. So it's always good to take a historical perspective on things. So everybody looks at 50-year anniversaries, and some of you were alive when in 1969 we had the lunar landing. So that happened exactly 50 years ago. So, you know, it was a very interesting piece. Neil Armstrong, of course, said the famous phrase, small step for a man and one gigantic one for mankind. But there was a second step that people forget, of course, that was that the command module and the module, the Eagle, had a digital computer. That at that time was something pretty new, and the design of that computer was done at not at Lincoln Lab, but a friendly competitor of MIT that is today MIT Draper Lab. So, but that's where it was done. And it had an unprecedented degree of integration for the time. 3 input norms that for that time it was something pretty incredible. If you read in the history, one of the reasons that they did this, it was the only way to understand what was happening with the digital design. It was about 2,800 of these Nord 3s with dual inputs and all that. When you look at the amount of memory and RAM and ROM that these machines had, it's pretty incredible that you managed to do what these machines did with such resources. But okay, that was 50 years ago. Where are we today, 50 years later? So if you look at the state of the art chip today, and these are the forensics done by Tech Insights, by buying an iPhone and slicing it very carefully. The last processor in an Apple iPhone is about 7 billion transistors. So if you divide by 6 on the NOR, it's 1 billion, the NOR 3s of the days of the Apollo, of the Eagle, 7 nanometer transistors. So it's a pretty stunning chip, of course, one of the most advanced ever made. And if you try to trace some of the areas, you notice GPU cores, some small cores, CPU banks, and also something that attracted a lot of attention, the one that is called the NPU for the neural processor, that is what gets used to recognize face shapes and other things. But significant progress in 50 years from the point of view of integrated circuit design. So today, if you look at the numbers, the scale is pretty astonishing. If you look at the 12-inch wafer, it has more transistors than the stars in the Milky Way, apparently by about an order of magnitude. So from the point of view of transistors, we're swimming in transistors, as you can imagine today. And these are, if you look at memories, is even more stunning. What has brought us here is interesting, the observation that was done really by Gordon Moore, one of the colleagues of Noyce at the Fairchild and Intel, that this was this statement that about 18 months or 2 years, depending on how you want to count, the number of transistors that will appear on the same area of silicon would double. So this was a very interesting piece. You can see today, now that everything has been put into electronic form, you can actually look at the original article that was in 1965. He extrapolated from 4 data points. And many of you probably have heard Gordon Moore speaking at many events, and He's a very nice, very humble person that he commented in one speech that everybody remembers his good predictions, but he made another. He says that, and he put a picture of himself with his prediction on the size of a silicon wafer, that at that time was, I think, 1.5 inches or something, and he had a picture of himself with a wafer as tall as him, that was his prediction. And he said, nobody reminds me of my wrong prediction, they were at 12 inches only. But anyway, so this has been pretty stunning, but the second part that people tend to forget a little bit is the end of the phrase, at the same manufacturing cost, meaning, and that's a very interesting commercial observation, that the area of silicon, the cost, let's say, of a square foot of silicon or however, I have a vacation home in Montana, they measure land in acres. In Palo Alto, the land is measured in square feet. So, depends that the area of the silicon was keeping the price constant. So you were getting twice the number of transistors for the same price. And that is a stunning decrease in cost if you can keep it. Today, where about if we start with the first generation in the 60s and we keep counting, today production is at 10/7. For those of you that follow the industry, I think TSMC reported yesterday or the day before their latest quarter, and they claim that about 10% of their revenue is 7 nanometers. That's also pretty stunning because it's probably a couple of chips. And they are already at that point. But let's say this is 2017, so let's say 2018 we have 7. So we have done pretty well in terms of scaling. So semiconductors, of course, continues to be an incredibly interesting industry, and this is more or less how the Semiconductor Industry Association likes to describe itself as the product of unfathomable advanced research and so on. It is an industry that is, as they say, not for the faint-hearted. This is more or less the revenue of the semiconductor industry, and you notice the ups and downs, and you can see here the dot-com bust in 2001, you can see the 2008 and 9 recession and so on. And in the last few years, we have seen a fairly exceptional situation. After 3 years of flat revenue, meaning plus minus 2% variation, in 2017, there was an increase of revenue of 22%. That for an industry that was already $350 billion, a 22% increase is a huge number. This year, meaning 2018, the final number is not there, but they have the numbers up to November, so the prediction is of the order of 15%. And that's what you see here. It will not hit 500 billion, but it will be relatively close. So that is not something, 20% increases per year is not sustainable at this scale. So the current predictions are sort of flattish, plus minus a few percent points. That on the one hand is always, everybody always wants to see more and more revenue, but obviously when you get stuck at a peak like that for a couple of years, life is not that bad from that. These 3 years, you were not hearing many bad things about the semiconductor industry from that perspective. So that's where we are today, and here you can see more on a quarterly basis how things oscillate, and the two big dips from the point of view of the dot-com bubble, that, by the way, for those that like predictions, because what is the famous phrase of Yogi Berra, to make predictions is very hard, particularly when you're talking about the future. But it took 4 years in 2000 to recover the level of sales in semiconductors, 4 to 5 years. And if you look at, on the other hand, the crisis of 2008, 2009, it was a deep but very narrow notch. It was much more a financial crisis than a supply crisis in some sense, so the recovery was pretty quick. And here you can see where we are today. You always get nervous when curves begin to approach vertical, because that tells you that something will not be sustained. But anyways, this is part of a little bit of Moore's law, in the sense that you see on one side the number of units that are being shipped, and the numbers are in the billions. This counts everything, meaning from the tiny resistors and all those things. And you notice that the selling price, the average, has remained fairly constant. If you look at it, there was a declining trend that was replaced by an uptick. And I believe that that's reflect the effect of memory prices in the last few years. That the memory companies, if you notice, did not sell much more in terms of units, but they could sell it at a much higher price. So you look today, companies like Hynix, for example, that 10 years ago it went almost broke. Probably it didn't go broke because the Korean government at that time did not allow it to go broke, and today is one of the 10 largest companies in terms of revenue in the semiconductor industry. Okay, so now let's take a look at how the technology is evolving. And this is a slide that I'm going to ask you to be a little bit patient with me, because this is an informal slide that always attracts a lot of attention in Wall Street for others. At Synopsys, as we have a very large presence as an EDA company, I'll talk a little about the EDA industry in a bit, we try to count designs to get a feeling for how new technologies are doing. And we try to count introductions of technology and try to count how many designs do we see in time. So you can see there that by near the end of 2005, we have observed somewhere between 400 and 500 designs in the world at 90 nanometer technology. That at that moment was the most advanced technology. This includes test chips, everything that we get a site that says company X is doing a chip called Y, we count it. Okay? Then we count at the tapeouts by that time. So there is a lot of design, and about half of them have tapeout. At that moment, we stop counting, because we say, okay, the technology has reached a level of maturity and use. It's not a new technology any longer, it has been established. So you have 90, you have 65 there, you have the first generation with high-k metal gate, the 4045, the tapeouts, then came 28 tapeouts. Oops, this curve looks very different. If you look at the difference between the peaks in time, it was about 2 years. Every 2 years, the new technology was reaching maturity. And suddenly, there was a significant change. In the yellow you see above, there was the 20 nanometer FinFET introduced by Intel. They call it Tri-Gate at that moment. The rest of the industry went to 20 with double patterning, so there was a divergence. And then things stabilized and people went to what some companies call 16, others call it 14 nanometer FinFET. But you notice that the spacing for the maturity of the technology increased significantly. So that was a very interesting change. And the other part, if you notice, is the following. Compare the difference between tapeouts versus designs at 90, that delta, and the difference between designs and tapeout in these technologies. The only explanation that I have for this is that these designs have become so expensive that you better finish it. If not, the company suffers pretty dire consequences. The number of cancellations of these chips that we used to see at 90, 65, for example, something gets started, never gets finished or so, was much larger than what we see today. And this is the 710, and there are a few brave souls doing 5. As you can see, we know design. There are not much in terms of, this is the tiny little corner here. So Moore's law continued to hold, in the sense that we continue to shrink and do this, but the timing has shifted quite considerably. Okay. So let's look now at how do you design, 10 billion, a chip with 10 billion transistors and all that. Of course, let's take a look now at what I've been working literally all my professional life, that is the EDA industry. So what we do is to try to, design software to help you design chips, and it has become something incredibly complicated. A brief history, we did, several of us taught a class at Stanford, so I'm acknowledging the borrowing of slides in here from my other two colleagues. The first time there was a conference in EDA was in 1964. For those of you that have white hair like me, they would remember the plastic sheets, the rudely drawn polygons, the Calma stations. Then some machines appeared to do this. Applicon, there were others. They were all using PDP-11s. As I work at digital equipment, but not of PDPs. That was before my time. Then simulators began to appear, and SPICE, that still exists today in many commercial incantations, was the first one of these that began to be used fairly heavily by designers. And there was a book that anybody that has an interest in a scientific book with incredibly influence in an industry should look at Mead Conway in '79, the introduction of VLSI systems. By the way, the last chapter on that book, that probably very few people even look at it, and there was a very nice chapter, is called Quantum Computing. When I saw it, I said, gee whiz, they were thinking about it already. Okay. Then the companies that appear would sell you a machine with the software on it, and that was Daisy, Mentor. They used Apollo workstations, some of them. In the mid-80s, actually all the computer companies had workstations, so that was the Microwax True from Digital that I knew well, and others. And that's where essentially Mentor was the only survivor of the old ones. And then Synopsys was founded, Cadence in '88. These were the things being done. The EDA consortium appears, and nobody paid much attention in 1990 to a small company in England called ARM. And that's when they appeared, and these guys were telling you, we can sell you the RTL of a microprocessor, and people would look at them like, you must be nuts, what am I going to do with this? But anyways, the industry kept growing. The big conference, that is the Design Automation Conference, peaked in attendance in the year 2000, 99, 2000, at about 20,000 people. Today is less than half than that, but it's a different life. And the revenue that this industry is generating, you begin to see it here. Place and route appears and became a commercial reality when 3-layer metals appeared. Cadence was the big winner at that time. To give you an idea of what the EDA industry has achieved in terms of enabling design, you can make a comparison between two, what you could say, whales of industrial design. One is a very complex SoC for a phone. Here is an older generation, but you can think that, okay, you have 4 billion transistors, it costs you between 50 and 100 million of engineering cost a year plus and all that. If you look at an Airbus 380, it has 3 orders of magnitude less parts, but the development cost and investment is astonishingly higher. We in EDA tend to think that one of the reasons is that EDA allows you to do a lot of these things, and the mechanical CAD and all that are still missing a little bit to get there. But anyways, that gives you some order of magnitude. The industry today, EDA, I mean, is incredibly concentrated. In reality, there are 3 big companies that are Synopsys, Cadence, and Mentor, and you can look at the numbers. Synopsys was 3.2 billion, Cadence is true. Mentor got bought by a huge German conglomerate, Siemens, so we don't see their revenue implicitly, but it must be in the order of 1.6, 1.7 billion. The little IP company that nobody paid much attention at the beginning was bought by this Japanese group, SoftBank, for the astonishing amount of $32 billion a couple of years ago, with a revenue of only 1.5 billion at that moment. SoftBank paid more for ARM than if they had bought Synopsys, Cadence plus Mentor at that time with that. And it's still a question mark how they are going to recover that investment. But ARM is doing well there. They are probably in the $2 billion range. ANSYS doesn't do the traditional EDA, is a company based in Pittsburgh, but they do some EDA, so we include it there. And Suken is a Japanese company that does printed circuit board EDA software that is about 200 million in revenue. So you can see it's a very, very concentrated industry. The real pure EDA companies would be those 3. So that's where we are. And this tells you a little bit of, you know, the pace of the designs as you get the chips and the sizes. And this we pick the family of Apple chips as it's easy to compare when they appear and they are the technology that they are implemented. In this case, you can see it a little bit more interestingly. If you blow up the chips to a 45 nanometer technology, that's how they would look, and with the A4 being 45. And here you can see a little bit the improvement in performance, and at the top is the number of devices, and Moore's law we have predicted a 1.4 factor, and it's a little bit better. I think the amount of cache, for example, helps in that sense, but holds pretty nicely from that perspective. EDA still, in spite that we're so concentrated, has an incredible number of very interesting problems that keep reappearing and that keep requiring new solutions. I'm going to give you a little bit of a flavor for some of the oldest one, that is, you have these standard cells that are these little boxes and you try to put them on a plane. Particularly, I'm addressing this to the students here. And you see that the dots show cells and the colors indicate the ability of the system to route to them. So if they're in red, no political connotations here, it's truly bad. You cannot connect to them, it's too congested. If they are green or very blue, they're really good. You can get there. This is two different placements with the same area, and you can see very easily that the difference in being able to route the design is pretty stunning between the two, and this has to all be done automatically. If you take a look, zoom in, this is how the dots would look, meaning the different cells have different sizes, but they are not that different. If you notice, probably it's a ratio of 1 to 10, they have uniform height. And if you zoom even more, this is the upper corner of the previous one, you notice that this placement is still pretty incomplete. They are overlapping and you need to clean it up significantly. So this would be what is called a coarse placement. And later you try to line it up perfectly, and this would be a detailed placement with many rules. The colors are different types of cells. The red and green is P and N sides of the cell. But if you look at this today, a small block is 1 million cells, a large block is 10 million cells. So the combinatorics of placement are against you, because if you simplify the problem, the number of arrangements that you could put on fixed sizes for n cells is n factorial. I went back to Wikipedia to take an estimate of the Stirling approximation. I even simplified it. E, let's say 3, 10 million divided by 3 to the power 10 million, obviously the combinatorics kill you instantly. So the number of heuristics and approaches that get used to solve this problem through the history of EDA has been a fountain of new development, from using mean cuts, simulated annealing, quadratic minimization, linear minimization, and other techniques. And as the blocks get larger and larger, we keep to refine and do more and more. Okay, still, even though we can handle those problems with today's computers, if you try to move yourself to other areas, you notice that the need for faster computers is pretty dramatic. One of the bad things of microprocessors today, and you notice it in the Apple chips, they have many more cores to perform computations, but the cores tend not to be fast. So if you wanted to do simulations, for example, what some of the people in the pharmaceutical industry try to do, simulate the interaction of a molecule with a drug and see how they would end up, it would take you so much time that faster computers would be needed. For those of you that like crypto security and all that, this RSA type schemes and all this public cryptography is based on the fact that if you want to factor one of these numbers with 600 plus digits, it would take you 1 billion years or something like that. So in other words, you cannot really do it. This is one of the impulses to look at very low temperature electronics, Josephson-Junction circuits, and eventually quantum computers to be able to tackle these problems. So there is a lot to do. I believe that in that sense, in spite of its ups and downs, the semiconductor industry will continue to do very well, and an industry that worldwide generates close to $500 billion, of course, provides a lot of employment throughout the chain. The EDA industry takes a tax of that, and if you look at more, the pure EDA industry is about 7 billion. So we take like 1.5% of those 500 million, and that pays us and the people that we employ. And if you added the IP and all that, the latest number I saw, even though I'm not sure whom are they including, it employs the commercial IP plus EDA close to 40,000 people worldwide. So on that part, every year grows a little bit, so the revenue for us in the industry for 3 years, so there is a good potential there and a lot of interesting problems to solve. So as Robert Noyce said, go off and do something.
It's a part of
that sense and
process where we take an orthogonal approach to the conventional simulations. Like in simulation, you apply inputs, you observe the outputs, you make sure that observed outputs are matching your expectations. Whereas the formal verification takes an approach where we mathematically try to basically prove that the circuit or the design that you're doing is basically correct. And the assertions and the formal technology comes into that picture. It has been growing industry or the growing technique. That's what I can say here. If any questions, I can answer.
Thank you, brother. My name is Ben. I also used to work for Synopsys. This is our conspiracy theory.
You seem to have like tentacles.
But anyway, I have been here for coming up 11 years. When I first started, I didn't think that would last that long, but I'm still here today. And I love it. I love it here. Currently, I work at Micron. I do verification. For those of you who didn't know what verification is if you design chips, you want to make sure that the chip works the way it's intended, and that's where verification comes in. And my sense is that it is good to be a verification engineer these days because they are in hot demand. I remember when I came here many years ago, verification as a profession did not exist at all. Things have changed since then. What I like teaching here is that I get to meet a lot of people, different kind of people, from someone who just graduated to someone who has been around for a while. So I get to see the whole spectrum and I get to talk to them. And some of them have become my good friends. So, yeah.
Hi, my name is Sam Huynh, and I teach 2 courses here. I did not used to work for Synopsys.
I'm surprised.
I did used to work for SGI, but currently I'm with AMD. The 2 courses that I teach here are the physical design course, which is the RTL to GDS flow using ICC from Synopsys. We go through the whole flow from floor planning to place and route, timing closure, which I'll get to in a bit, and follow with physical verification and, in the end, tape out to the foundry. The second class is timing closure, which focuses specifically on that one aspect of the physical design flow of timing closure, which is to basically make sure that your design meets certain timing specs, basically clock rate frequency. And that is a separate course from the physical design course. There are 2 basically compatible courses to form a set, and they're both introductory classes. The intent is really for people who are not familiar with physical design to get started in the physical design field, and also for a lot of RTL designers. Previously, RTL design and physical design were 2 separate sides. They write an RTL and then they dump it over the wall. But the complexity of modern designs, as Dr. Domic has shown, RTL design is much tightly coupled with physical design. If we don't combine the 2, then it might be very difficult to actually meet certain timing characteristics and meet performance requirements. So as a result, it's also targeted for RTL designers who like to get an understanding of the impacts of physical design and timing closure.
Thank you. So my next question for the panel, what are the common careers that are in your field that you have either experienced, observed, or you think still need to happen?
Sure, I'll start. I think first of all is the complexity of the modern day ASICs requires that we can't do things manually. It has to be done with EDA and has to be done at a relatively larger scale. Blocks of 1 million transistors, or blocks of 1 million gates, which translates to effectively 4 to 6 million transistors, are very common. And so on any given SoC, there could be 60, 70, or 100 blocks, which comprises like a 4 billion transistor design. So as a result, we have to understand the physical design from RTL to GDS, which basically means that for within a short period amount of time, a given year, 6 months, 9 months, we have to go from a physical net list to an actual GDS to tape out the foundry in order to meet market. So that's one thing, is physical design is a very hard commodity right now. I know a lot of ASIC companies are always looking for good physical design engineers. Secondly, that ties in with time enclosure. So it's not just you run through place and route and get a block, and then, hey, it's physical verification clean, I'm done. But it also has to meet certain timing characteristics. And so that also comes into play as well. So time enclosure is also very important because, as we understand, performance is key to products in most cases. As a result, time enclosure and also physical design combined is a very in-demand skill set as of right now.
I can say something. One very typical complaint, in a sense, that I hear from a lot of our customers, the designer tells me, I don't design anymore, I tweak your EDA tools because they never do what I want. So, okay, I take it as part of the industry, but this couples to your comment that is the following, that when you're doing chip design today, the tasks are not as separated as they used to be. So what you are putting in the architecture, for example, trying to see if you are partitioning certain functions this way, how many wires are going to be running so that they can be routed later, and all those pieces. So one of the things for me that I believe chip companies are looking at it is that on the one hand, of course, there is all the basics of engineering and everything, but not only running the tools and knowing how, the options and all of that, but for me, some understanding of what are they doing. We always get informal verification complaints, even in the oldest area, like equivalence checking, why the hell I gave the tool true circuits to prove that they were the same and it blows up. And then to know that a tool builds certain graph structures inside, that multipliers will blow up certain memories and all of that. A better understanding of the algorithmic insights of these things have become, in my opinion, pretty fundamental. Now, people who really like the algorithms and all of that, can go to work at Synopsys, hopefully, or Cadence, Mentor, and others from that. But I believe that this extra understanding that this is happening, why, what are we really doing wrong, more for the internals of how the algorithm operates and all that has become much more necessary for the chip designers than it used to be 15, 20 years ago, for example.
Anyone else?
I'd like to share some of my experience here, both working in the Valley and for the last 10 years teaching here part-time as part of the UC Extension. So kind of give me a flavor of looking at both sides of the equation. So most of my students, they show up and they range from a new college grad to someone who has been in the industry for 20 plus or 30 plus years. What I realized is that the Valley goes in cycles. At one point, when technology is hot, the next year technology moves on, and then in 5 years, a different technology emerges. I remember when they came here in the 90s. Who was here in the 90s? So you kind of knew what was going on, right? So I remember when I came here when I was looking for a job. In the mid-90s, when you look for a job, you don't even go to Google. ago didn't exist yet. We bought San Jose Mercury News, Sunday edition paper, right? It's about 5 inches thick. You look at the classified section, and then you spend your Sunday morning with a cup of coffee, you flip through the classified ads. The hardest job during that time, if you were in the semiconductor industry, was a title called design engineers. They were the highest end jobs that you could possibly get in the early to mid-90s. If you tell your mother-in-law that you were a design engineer, you'll be in a good graces. But things change. When you move from mid-90s to the early 2000s and then to the mid-2000s, in the process of designing complex chips, designers run into problems that they didn't encounter before. When the design gets so big, there are so many IPs, the problem emerges such that nobody really knows what's going on in the chip. No one person knows what's going on. There was a huge undertaking to make sure that the chip works the way they intended. So the problem that emerges is also good opportunities because people were trying to solve a problem that they never had before, and that problem was verification. And in fact, there was a standard that was developed, and it became system rollout in 2005. So one of the type of problem that people are trying to solve today is verification problem. And with that problem comes opportunities. Verification is one of the most abundant jobs that you can get nowadays. If you look at LinkedIn and you look at other job boards, we can't hire verification engineers fast enough. If you know verification really well, you get snapped out right away. So that's the trend that I'm seeing right now. It may change 5 years from now, it may change 10 years from now. One of the things that I always discuss with my class is that if you want to look at where the employment opportunity is, look at what the problems are. Because people hire engineers to solve problems. If there's no problem to be solved, then there are no jobs for you. So those are some thoughts that I thought are very interesting to look at. And I assume that most of you are here, besides the free pizza and the free drink, is want to make some connections, right? You want to get to know people so that it may lead you to something that you want to look at later on.
Just to kind of carry that theme about, I think Ben made a good point saying, look at where the problems are, right? And just if you look at one of the problems really in a kind of a chip design kind of an area is that there is a lot of software now is on the chip. Chip is no longer just a piece of silicon. There is a lot of software that gets, and this kind of like a firmware embedded system plus the silicon. That is now kind of your new thing that you need to kind of make sure that everything works as expected. So, and that's where if we see the traditional way of looking at applying the inputs and looking at the observation point is no longer applicable because you don't know what the software is going to do on your chip. And now how do you basically make sure that whatever software does, you don't basically create any fatal scenarios with your chip? That's the kind of the next challenge really. It's all part of the verification, and since you cannot anticipate what really is going to cause it, you have to do it mathematically. And that's where I guess the formal comes into the picture. So that's kind of the new area, and not necessarily the current tools are able to solve that problem, but unless we exhaust the tools, the new tools are not going to emerge out. So it's interesting times, for sure.
Thank you. So my next question, beyond the technical skills that are needed for someone to be successful in the field, what are the non-technical skills, for example, business-related skills or soft skills that someone would need to be successful? So things like budget and workforce planning, being able to work well on the team, being able to work in long-term isolation for a while, critical thinking. What kind of non-technical skills would someone need to be successful?
Just if I can take that or start with that. non-technical skills, soft skills as you call it, definitely are essentials. No person is an island. You cannot just say that, okay, I'm going to just do my job in an island. You are always going to interact, whether you are a verification engineer, physical designer. If you see everywhere there is like a mesh, right? Like the physical designer has to know what the chip is going to do. You cannot just say that, okay, I will just work with these transistors and place them in this box. And the architectural design cannot just design without thinking about the repercussions of what is going to happen in the silicon. And so that's where basically the communication is one of the soft skills. Like how do you communicate your ideas, right? Like, or what you think, how you can go across the different people who may not have that expertise, and how you can basically relate to them, or how you can explain to them like a congestion problem, how you are going to tell that congestion problem in the silicon to an architecture basically who is coming up with next Solana kind of thing. So in that sense, basically having strong communication skills and working with the team definitely is an essential part of today's workforce.
Yeah, I would agree. I mean, when you look at, you were mentioning timing analysis. A timing analysis tool today is 2.5 million lines of code. So you're not going to write it by yourself. It's going to be a team. Your tasks are going to be divided. You have to be effective in terms of working with the others and all of that. That for me is fairly critical, and also, I mean, one thing that you hear it in many different ways. I'll say it my own way from my own experience. Suddenly, you end up yourself being the head of a team. Usually, you begin is 3, 4, 5 people, but then when you have a very small team like that, you can know almost as much as everybody in the team. When you get 10 people, you have to be able to understand that I would not do it exactly that way, but that's a very good idea. I should let them do it. Like how do you balance, the control and feeling in a way that also the different people that will know more about the subject than you do, and forget it when you have 100 people, that you are going to know more than each of them on any topic. Being able to leverage the different parts and exercising good judgment on, but as I look at myself, it always goes, I wouldn't do it exactly that way, but looks like a very good idea. They should do it. It's a very important part so that the teams will grow, and if you want to go into technical management in particular, I think you have to get used to that fact that you're going to have people that will know more than you about the part of the problem.
So I will just add a couple of comments to both what they said. It's absolutely true. I think from my own personal experience, some of the toughest things I have to deal with is having someone try to explain to me their thoughts and me not understanding what they're trying to tell me. So I think one of the soft skills is, as an engineer, if given a task, it's more than just your job. You should own that task and understand that inside and out, so that it's not only for yourself, but so you can explain to others around you, to people you work with, or to either your upper management or to your other teammates, to make sure that they too understand what it is that is the problem and what it is that is your solution. A lot of times it's that communication that's difficult to. What are you trying to tell me? What is your solution? And that to me is one of the soft skills that I think you should have to be very successful.
My thought is that when I first started many years ago, someone told me that if you're an engineer, all you need to do is you look at the computer, 8 to 10 hours a day, do your thing, and you'll be good, right? And I quickly realized that if I do that, I'll be heading out the door very soon. What I find very interesting over the years is that I start interacting with different people. It's a skill as much as it is an art when you start dealing with people. And when you start dealing with people, you're dealing with a whole spectrum of people, from someone who just graduated, to someone who is mid-career, to someone who is in their 60s and 70s. And you add on top of that, with the explosion of globalization, most of us have to deal with offsite design, right? India, China, maybe Europe, maybe in some other far-flung places. And it can be a challenge, because if you deal with places like India, they have a different culture, they have a different work environment, versus if you deal with people from Asia, Japan, China, Korea, right? They are all different. And if you think that you tell them something explicitly, they may or may not get what you're trying to tell them. Vice versa. When they explain something to you, what is said is as important as what they didn't say. So I think it's a learning process, at least for me, and it continues to be a learning process for me every day. To try to understand what they're trying to communicate to me, not just in words, but in what they're trying to say without saying it. And I guess that's also true when I deal with my colleagues here at different levels from different organizations. The message that comes with what they're trying to tell me, I think sometimes you go a step further and try to understand what's behind what they're trying to tell you. It really opened a whole new world for you.
Wonderful. Well, thank you so much for sharing your expertise and your experiences. We hope that this will not be the last time you have an opportunity